Episode 1. What pigments really do inside an automotive coating film. In this episode, we establish the fundamental understanding of what pigments actually do inside an automotive coating film, beyond simply providing color. This foundation is essential because every visual, mechanical, and durability-related property of a paint film is directly or indirectly influenced by pigments. An automotive coating is a multi-phase system. Once the coating is applied and cured, the film consists of a continuous polymeric binder phase and a dispersed solid pigment phase. Pigments are solid, insoluble particles that remain physically embedded within the binder matrix. This insolubility is a defining characteristic and is what differentiates pigments from dyes. Because pigments exist as discrete particles, their size, shape, surface chemistry, and spatial distribution inside the film become critically important. When pigments are first introduced into a liquid coating system, they exist as large agglomerates held together by van der Waals forces and, in some cases, electrostatic interactions. The dispersion process applies mechanical energy to break these agglomerates down into smaller aggregates or ideally primary particles, while wetting agents and dispersants stabilize the newly created surfaces. If this process is incomplete, pigment clusters remain in the film, leading to poor color development, reduced hiding power, surface roughness, gloss loss, and long-term instability. The primary function of pigments is defined by how they interact with light. When light strikes a coated surface, part of it is reflected at the air-film interface, part enters the coating, and part is either absorbed or scattered by pigment particles. The balance between absorption and scattering determines the perceived color, opacity, brightness, and depth of the coating. Color pigments function mainly through selective absorption of visible light. Their molecular structure allows them to absorb specific wavelengths while reflecting others. The reflected wavelengths define the color perceived by the human eye. The strength and purity of this color depend on the pigment's intrinsic absorption characteristics, as well as its dispersion quality. Poor dispersion reduces effective surface area and lowers color strength. White pigments operate on a completely different optical principle. Their main role is not absorption but scattering of light. Strong scattering prevents light from penetrating through the film and reaching the substrate, thereby creating opacity. The efficiency of light scattering depends on the refractive index difference between the pigment and the surrounding binder. Titanium dioxide is the most effective white pigment because its refractive index is significantly higher than that of organic polymer binders, making it extremely efficient at scattering visible light, even at relatively low concentrations. Black pigments, particularly carbon black, rely primarily on absorption across a broad range of wavelengths. This results in deep black coloration and strong UV absorption. While this UV absorption can protect underlying layers, it also leads to heat buildup, which must be considered in automotive applications where thermal stability and dimensional control are important. Beyond optical effects, pigments play a structural role in the coating film. Once the binder cures, pigment particles act as rigid inclusions within the polymer network. They influence mechanical properties such as hardness, modulus, scratch resistance, and resistance to plastic deformation. Proper pigment binder adhesion is essential. Weak interfacial bonding can lead to microcracking, reduced impact resistance, and premature failure. Pigments also affect barrier properties. A well-dispersed pigment system increases the tortuosity of diffusion pathways for water, oxygen, and corrosive ions. This slows down transport through the film and improves corrosion resistance, particularly in primers and functional layers. Conversely, poorly packed or overloaded pigment systems can create voids that accelerate permeation. Surface chemistry is another critical factor. Pigment surfaces may be polar, nonpolar, or chemically modified. Surface treatments are commonly used to tailor pigment, binder interactions, improve dispersion stability, and reduce undesirable reactions with curing agents. The choice of pigment surface treatment must align with the resin chemistry of the coating system. Particle size and size distribution strongly influence performance. Smaller particles provide higher color strength and smoother films, but have higher surface area, increasing binder demand and viscosity. Larger particles are easier to disperse and more stable, but may reduce gloss and distinctness of image. Automotive coatings require a carefully optimized balance between these competing effects. Pigments also influence application behavior. They affect viscosity, flow, leveling, sag resistance, and spray atomization. In the case of effect pigments such as metallic flakes, orientation during application becomes critical, as it directly determines visual properties like brightness, flop, and color travel. Finally, pigments are a major determinant of long-term durability. They must survive UV radiation, thermal cycling, chemical exposure, and environmental weathering over many years. Some pigments are inherently stable, while others rely heavily on protection from the binder system and additives to maintain performance. In summary, pigments are not passive colorants. They are active, multifunctional components that control optics, mechanics, durability, and application behavior of automotive coatings. Understanding this role is the foundation for everything that follows in pigment selection and formulation design. If you have any doubts, questions, or want deeper clarification on any part of this episode, share them in the comments and let me know.